All right, in this problem, a man or a trampoline artist jumps upward vertically from the top of the platform with vertical speed of 4.5 meters per second, and we are supposed to calculate the speed of this person when he lands on the trampoline. So in this case, we use a model. So let's say here is the platform, and here is the ground, and here is the trampoline. So the distance from the top of the platform to the top of the trampoline is 2 meters. And the person we just model, the person with a just mass m, which is 62 kilogram. Then this has the velocity of vertical velocity of 4.5 meter per second. Then it goes up a little bit and comes back at this point. So let's set this point as the initial point. So we'll call this point initial point, which is here when getting back to the same level of the platform. So at this point, the velocity of this person is 4.5, but with a negative direction, because when it gets to the same point, the velocity will be the same, the magnitude, but the direction will change. So here the velocity is minus 4.5 meter per second. And then it reaches the surface of the trampoline. So we call this surface as final position or final. And what is the reason we are just denoting, or we are just calling or marking as initial or final? Because we need to solve this problem by using the law of conservation of energy. And the law of conservation of energy states that the initial mechanical energy will be equal to final mechanical energy. And here we do not have any air resistance or any friction, so therefore the mechanical energy will be conserved. So let's calculate the initial mechanical energy. What kinds of energy does this person have when it reaches the initial point? So at this point, this person has velocity, therefore it has kinetic energy. And also, since we have already set our, so let's say this is our frame of reference or reference frame here, this point, so this point is 0. So therefore, since this person has height is above this level, this 0 level, it has also potential potential energy. So therefore, the initial mechanical energy includes, here in this case, kinetic energy plus gravitational potential energy. So this is initial mechanical energy. But when the person reaches to this point, so it goes down, reaches here, at this point there is no any height between them. It's not above the ground, it's exactly at the 0 point. So therefore there is no gravitational potential energy, and only there is a kinetic energy. So this will be a half of mass times velocity squared. But the velocity at this point is different from the velocity at the beginning. So we just substitute the numbers or plug in the numbers into the formula, and then we will get the final velocity, as simple as that. So therefore it will be a half of 62 kilogram times, the velocity here is negative because the direction is downward, so to the power of 2 plus 62 kilograms times 9.8 meter per second squared, which is acceleration due to gravity. And then the height is 2 meters. And the other side of the equation will be a half of 62 kilogram times final velocity squared. And then by solving this problem, we will get the final velocity must be equal to 7.71, and the direction is negative. Okay, that must be negative meter per second. So that is the answer for part A of this problem. So negative or minus 7.71 meter per second is the velocity of this person that reaches at the surface of the trampoline. But part B asks what if, how much, because the trampoline is like a spring, so it says how much it is compressed, how much the trampoline compresses when is compressed when the person lands on that. Okay, so again we will let's again draw the model here. So this is the platform again, and this is the ground. This is the trampoline, and then here is 2 meters. And let's say trampoline will be like that, because the person lands on it. So when it lands on it, it will be compressed. Now here we want to calculate the how much this compress is. So let's call this compressed part as h. So the distance from the surface of trampoline to the distance actually that it is compressed. So we call it h. So that is the h is the displacement that this spring makes. And now again we will use the same law of conservation of energy, and we will follow the same thing. But here there is a problem, and the problem is where to set our frame of reference, where to set it. So we have calculated the energy of this person at this point. So we have two ways actually. We can set the initial position here. This is initial, and final here, because we already have the kinetic energy at this point. Or else we can just say, no, we keep the previous initial position as here. So this is initial position, and then this time I will set the frame of reference at this point, the compressed point, okay? So this will be the zero level, or the frame of reference here. Then, in this case, we can say, so here is final, and initial is the same position. Now, let's go ahead and solve this problem. Let's see what we can do here. Again, I will say energy is conserved. It means the sum of all types of energy at the beginning must be equal to the last of the last position, at the last position. So here we will say at the initial position it has the same level of energy, so it has a half of m v initial to the power of 2 squared plus potential energy, and potential energy here is mgh. But what is h? H is it 2 meters, or if you notice, h here is no longer 2 meters. It is more than 2 meters. So if we say we take our h for the gravitational potential energy from this point to this point, we will see is no longer 2 meters, because from here to here is 2 meters. But it has something more, so therefore it will be 2 plus h meters. Okay? This will be 2 plus h meters. And therefore we write 2 plus h, and then is equal to so when the trampoline is compressed, what kind of energy do we have got here stored? Actually, we have an elastic potential energy. So therefore, the elastic potential energy will be a half of constant of the spring times x squared, which x squared, since it is towards the vertical axis, let's correct it and change it to h, and this is the real h because the displacement that this spring makes, okay, the amount that it is compressed. So then we replace them with numbers, nothing more. We replace them with numbers, and then we will get to this equation, which is 29,000 h squared minus 607.6 h minus 1842.94 is equal to 0. As you see, we have got a quadratic equation here, and by solving this quadratic equation we will get the answer, which the answer is, we will get two answers actually, because it has two roots. So one is h is negative 0.241 and the other one is 0.2627, which we take this one as the answer because it is positive. So this will be meter, and the unit is meter because our calculation were all standards are units. So this will be also in meter. Okay, thanks for watching this video. This is the solution for this problem.